Hello students, welcome to the classroom point. In today's session, we shall discuss the concept ozonolysis. If you like my explanation, please do subscribe the channel. So when come to the point here, ozonolysis means it is the addition of ozone to an unsaturated molecule. So here unsaturated molecule means it may be alkene or alkyne molecule is called as ozonolysis. And the intermediate compound that is formed in this process is called as the ozonide. When it comes to the types of the ozonolysis, it is of two types. One is the reductive ozonolysis, in which we use the ozone followed by the reaction with either zinc water or dimethyl sulfide. Second one is oxidative ozonolysis, in which again we add the initially ozone followed by the reaction with the either hydrogen peroxide or silver oxide. Now, here, if you take the alkene molecules, so you must remember one thing, that whenever I am using the word in the case of the reductive ozonolysis means any of these combination of the chemical compounds we are going to use. For oxidative ozonolysis, these are the compounds we are going to use. So in the case of the alkenes, alkene generally a double bond is present between the two carbon atoms. That molecules are called the alkene. So when it is subject with the ozone, it forms a 5-membered ring that is called the ozonide. So here you need to do one thing, that break this double bond, put one oxygen here and two oxygens here and connect all these through carbon atoms. And this ozonide, when subject with the reductive ozonolysis, means just you add the zinc H2O or dimethyl sulfide here, then you will get the carbonyl compounds. That means it may be aldehyde or ketone depending on the type of the alkene molecule we select here. And if you use the oxidative ozonolysis, means to this ozonide, if you use hydrogen peroxide or silver oxide, because ozone already added here in both these cases. So in the case of the oxidative ozonolysis, this particular alkene molecule usually produces carboxylic acids and ketones. I forgot to write down here. I will mention here it is the ketone. So no aldehyde compound will be formed. Why? Because whatever the aldehyde compounds are formed, that aldehyde compounds will be oxidized by the hydrogen peroxide to the carboxylic acids. So that is the reason why in the case of the oxidative ozonolysis of the alkenes, we get either carboxylic acids or the combination of the carboxylic acids with the ketones depending on the type of the alkene molecule we select here. Now let us take the some compounds here. When a double bonded carbon atom in alkene is connected to the two alkyl groups, so whether you subject that particular part with either reductive ozonolysis or oxidative ozonolysis, you get the ketone. Means this particular carbon will be connected to the one oxygen molecule giving the ketone part. But when it comes to the alkene molecule in which double bonded carbon atom is having at least one hydrogen, here one hydrogen atom is there, here no hydrogen atom. So if at least one hydrogen atom is there, in such cases, if you use the reductive ozonolysis process, this particular double bonded carbon atom with the hydrogen will be converted to the aldehyde. But in the case of the oxidative ozonolysis, this particular double bonded carbon atom with the hydrogen will be converted to the carboxylic part. Now, if any alkene is having the double bond CH2 group, reductive ozonolysis gives formaldehyde, whereas oxidative ozonolysis initially gives the formaldehyde. That formaldehyde will be oxidized to the formic acid. Again that formic acid will be oxidized to the carbon dioxide. So wherever double bond CH2 is there, in the case of the oxidative ozonolysis, you just write down the carboxylic acid, carbon dioxide part from that particular part. Now let us see some of the examples here. So this is the one molecule. So in this molecule, you see here, this is the carbon with hydrogen. This is the carbon without hydrogen, double bonded carbon. So when you subject with the reductive ozonolysis, this you break this bond, put oxygen here, here one oxygen, so that you will get the CH3CHO acetaldehyde, CH3CO CH3 acetone. But in the case of the oxidative ozonolysis, this particular double bonded carbon atom with the hydrogen will be converted to the carboxylic acid, and this shall be converted to the ketone. Now let us see another example here. So this is the molecule where double bonded carbon atoms, both of the double bonded carbon atoms are having the hydrogens. In the case of the reductive ozonolysis, they give the aldehyde. So here one oxygen, break this bond and write down CH3, CH2, CHO. So we will get the both are the aldehyde molecules. But in the case of the oxidative ozonolysis, both of these carbon atoms will be producing carboxylic acid molecules. Let us take another molecule. In this particular alkene molecule, subject this one with the reductive ozonolysis. In the case of the reductive ozonolysis, only one thing we have to do is just break this double bond. Put oxygen here and one oxygen here. So it becomes CH3COCH3. That is acetone molecule. CH2O, which is called the formaldehyde molecule. But when you use the hydrogen peroxide or silver oxide in this particular ozonolysis, which is called the oxidative ozonolysis, as I said earlier, so here it becomes the CO part, because carbon with two alkyl groups of double bonded carbon with two alkyl groups always will be converted to the keto group, whether you use the reductive ozonolysis or oxidative ozonolysis. But at least any double bonded carbon atom is having at least one hydrogen will be converted to the carboxylic acid or carbon dioxide based on the type of the double bonded carbon atom and number of the hydrogens present over that double bonded carbon atom. Here this CH2 will be converted to the formaldehyde in the case of the reductive ozonolysis, but in the case of the oxidative ozonolysis, this shall be converted to the carbon dioxide. Now, let us take one of the important compound which was asked in the previous examination, that is benzene. So, this benzene on ozonolysis gives, see here 3 moles of ozone we use it. So, break this bond, put one oxygen here and two oxygens here and connect this one. Break this double bond everywhere like that. So we get this molecule which is called the benzene triozonide. Subject this one with the reductive ozonolysis. So in the case of the reductive ozonolysis, we have to do the things like this. You break the bonds like this. So here hydrogen is present. To this carbon atom also hydrogen is present. Now this gets CHO and here also CHO. These both CHO groups are connected by the one single bond. So CHO with CHO. Like that, here also CHO and CHO. Here also CHO and CHO. So we get the 3 molecules of CHO which is called the glyoxal in the case of the reductive ozonolysis. But the same glyoxal will be formed even in the oxidative ozonolysis also. But hydrogen peroxide will oxidize this CHO group to the COOH. Hence, we get the oxalic acid molecule in the case of the benzene molecule. Now, let us see how the ozonolysis process takes place in the case of the alkynes. So, alkynes on reaction with ozone gives ozonide. This ozonide on oxidative ozonolysis, we must remember one thing, that hydrogen peroxide, silver oxide acts as the oxidative parts in the case of the alkenes, and dimethyl sulfide acted as reductive part in the case of the alkenes, but this dimethyl sulfide is also acting as the oxidative ozonolysis part in the case of the alkynes. Gives carboxylic acids. And on reductive ozonolysis, so in the case of the alkynes, reductive ozonolysis is confined only to the zinc and H2O. So here we forgot to mention zinc plus H2O. Okay. So now let us see when on reductive ozonolysis it gives dicarbonyl compounds. Let's see some molecule. This is the alkane molecule. So this alkane molecule on reaction with the ozone, it gives ozonide. And the difference between this ozonide means alkene ozonide, you see here one important thing. In the case of the alkene ozonides, there is no bond between the two carbon atoms in the ozonide. That is called the alkene ozonide. But in the case of the alkyne ozonides, there is a bond between the two carbon atoms in the ozonide. That is called as the alkyne ozonide. So this type of the ozonides are always found from the alkynes. So in this case also, alkynes having alkyl group means triple bonded carbon, if it is connected to any alkyl group, undergo oxidative ozonolysis and this particular carbon will be converted to the carboxylic acid. But in the case of the reductive ozonolysis, this shall be converted to the only C double bond O part, continuing the next valency to the chain. And if any triple bond CH means terminal alkyne group is there, oxidative ozonolysis gives carbon dioxide, except in the case of the acetylene that we shall see here, and reductive ozonolysis will convert the CH part to the CHO. Let us see in the case of the acetylene, both are the terminal CH groups are present. So if you use the oxidative ozonolysis, this initially will be converted to the glyoxyl, means this will be converted to the CHO like in the reductive ozonolysis, but the presence of the hydrogen peroxide converts this particular glyoxyl to the formic acid later using the hydrogen peroxide. And in the case of the other type of the alkynes, if you take this is alkyne where triple bond CH is present and triple bond carbon with one alkyl group is also present. Now you take the oxidative ozonolysis. In the case of the oxidative ozonolysis, this part means you just break the triple bond between the two carbon atoms. So this particular carbon with alkyl group will be converted to the carboxylic acid, and triple bond CH will be converted to the carbon dioxide. And if you use the reductive ozonolysis, so in the case of the reductive ozonolysis, this shall be converted, means one bond still present between the triple bonded carbon atoms, only two bonds will be broken. So here it forms the keto part, and this shall convert the CHO part. Now you take the another molecule, this is the internal alkyne where there is no triple bond CH group. Use this one oxidative ozonolysis. So in the case of the oxidative ozonolysis, you must think that dimethyl sulfide also gives the oxidative ozonolysis products. So break this bond, convert this both of these triple bonded carbon atoms to the carboxylic acid, so that you shall get the CH3COOH, CH3COOH like this. Both are acetic acid molecules. And if you take the reductive ozonolysis part, then both will be converted to the double bond O, means keto groups, and because still there is a bond between the two triple bonded carbon atoms in the final product, so that only two pi bonds will be broken and they will be converted to the carbonyl part in the case of the reductive ozonolysis. Now let us take the final example for this one. This is a general example. Use ozone with dimethyl sulfide. We know that dimethyl sulfide, in the case of the alkenes, it acts as the reductive part, and in the case of the alkynes, it acts as the oxidative part. So that here, if you observe, double bond alkene part is there, triple bond alkyne part also there. So when ozone dimethyl sulfide combination is used to subject this particular molecule, only in the case of the double bond, it acts as a reducing reductive ozonolysis part. So these shall be converted, these will be broken into the aldehyde and keto part. Both are carbonyl groups. And in the case of the triple bond, it acts as the oxidating ozonolysis part. So it breaks this bond and convert these triple bonded carbon atoms to the carboxylic acid. So that is the reason why here this particular part we get the CH3CHO, and this particular part will be converted to the CO part, and here this shall be converted to the COOH part, and this also shall be converted to the COOH part. Thank you dear students. If you understand my explanation, please do not forget to like the video and subscribe the channel. Thank you.